basically saying like I record you without like consent, but I don't show any student on the recording, so it doesn't really matter.
Is it if someone speaks, then you hear them?
Yeah, but I don't know if I have it set up to like transfer camera whenever somebody speaks.
Nobody talks.
There's also that. Thanks, Jack. I appreciate the energy though. At least Chem Large Group was just like pulling teeth. It was miserable.
Last week?
No, an hour ago.
Oh. That's how I remember.
They just like they are
Is
just.
it a really big group again?
I mean, it would be, but
Well, okay, yeah. I guess
we
that's
still have like almost 45, 50 kids up there. We're the biggest large group during quarantine or during this.
So you went back to being a chem teacher, and is Miss Reed also one, or did she?
No, so prior to last year,
It was you and Shia.
me and Shider for the 4 years before that.
But
Then
you got
last
too
year
many.
I had way too many AP Chem kids. Then I just went strictly to AP Chem. And then this year I picked up a section of Chem.
Oh, so what about Reed? She's still.
We didn't have the numbers, so Reed's doing ag and freshman science,
Oh, okay.
which is normally her classes.
Okay.
All right, I'm going to teach things. We're like 3 minutes in. Today, we are going to learn about titration. You learned this last year, kind of like everything else we've learned in Unit 4. Remember when I said Unit 4 was going to be nice? I meant it. It's going to be pretty nice. And guess.
I don't trust you. Wait, is this the pink stuff?
He's so hurt.
I am so hurt. You don't trust me as an educational professional?
It's not you personally. I mean, I've seen Breaking Bad. I don't know.
Wow, that far? That far? Jeez.
Is this the pink stuff though? Like,
You know, yeah, we'll get to that. Okay, so after titrations and acid-base stuff in Unit 4, we're going to go to redox stuff.
yeah.
That was when everything fell apart, wasn't it? Or was it before? Okay, redox is the best. So I'll get super pumped for those days, and you guys will be good to go. All right. So let's learn about titrations a little bit. The objective listed today is to identify the equivalence point in a titration based on the amounts of the titrant and analyte, assuming that the titration goes to completion. So again, vocabulary of this class gets a little funky. We'll define what titrant and analyte are in just a second, and it's not anything too complicated. But anyway, so here's how a titration looks. You ran some of these last year, if I'm not mistaken. This was pre-shutdown, I believe, right? So you ran a titration. The burettes are on the back wall, okay? Those are nice burettes. We bought those after I got hired because the ones before I got hired were absolute garbage. And those are about 80 bucks a piece. Okay, so that's like more than 80 bucks. Just doing quick mental math. So this is the setup, right? We have a burette, is what it's called. A burette is kind of like a backwards graduated cylinder. If you remember reading those last year, the numbers go down. 50's up here, 0's down here. Does that ring a bell?
Yeah.
Okay. So we have a burette. There is a chemical in the burette, normally an acid or a base. And then down below, we have an Erlenmeyer flask right here. And in the flask is the opposite, right? If I had an acid in the burette, I would have a base in the Erlenmeyer flask. If I have a base in the burette, I would have an acid in the Erlenmeyer flask, okay? And when I open the burette and I'm releasing the titrant into the analyte, okay, they react, and they react, and they react, and they react until what happened? Jack! It turned pink. But maybe,
I thought we were trying to get rid of it.
depends. It could be either which or, right? It depends upon which way you're going. We'll talk about that a little bit too. But it changed color. Let's say it that way, because then it covers both of our bases.
Can it be another color? Like
Absolutely. Yep. Absolutely. Yep. So there's way more than one indicator. We make it seem like there's only one because everything we ever taught you was with phenolphthalein. But there's way more than one indicator out there in the real chemistry world. So it changes color, right? Now, what the color change means is at that point, in theory, we have equal moles of acid and base added. And we've completely neutralized what we have there. All right? We'll talk more about that too. Let's get some definitions though. Oh, not yet. I'm sorry. Gosh darn it, there's always one more slide. My transitions are garbage. Ah, I should just retire. Be nice.
We get the AP Chem credit and you're tired, we're done. I think that.
Shake on it, deal. I'm in.
I can use some.
I don't got the money to retire though. I better keep working. Okay, titrations can be used to analyze multiple types of chemical reactions. Okay, what I just described on the previous slide and what you did last year was acid-base. We will, or I will, maybe you will. I don't know. We'll see how we can do a lab here. But eventually, I'll run a redox titration as well. It doesn't just have to be acid-base. You can use titrations for more than acid-base chemistry. Okay. I have the other examples I have here are precipitation reactions and metal complex reactions. Don't worry, we don't talk about metal complexes all year, and I didn't learn about those until my junior or senior year of college, so not going to be a thing. But it is a thing in the real world. So regardless of the type of titration you're running, the overall concept's the same. You know the molarity or the concentration of what's in the burette. You don't know the molarity or the concentration of what's in the Erlenmeyer flask. We use the known molarity of the titrant to analyze or discover or determine the molarity of the analyte, what's in the flask. So I know half of the stuff, right? That's the whole point of running this type of experiment. I know the molarity of what I'm adding, but I don't know the molarity of what I'm adding it to. And the goal of this lab, or the goal of a titration, is to figure out the molarity of what's in the flask. Okay? So now, let's do some definitions. Titrant. This is the chemical solution added from the burette. Whatever is in the burette is called the titrant. And burette is spelled more than one way. I've seen it B-U-R-E-T, and I've seen it B-U-R-E-T-T-E. Depends upon whether you prefer the Frenchy version or the other version. They both are accepted. I kind of like the Frenchy version. E-T. So I'd chop off the last two letters here.
Oh, so like you prefer T?
No, I prefer like I have it written.
Oh.
I feel like it makes more sense, like phonetically almost.
You follow up that? Yeah, that does make
Yes, I do.
Isn't that new, the bottom one?
Yeah, Schradler made that.
sense. Is that because you fell too many times?
I think so, or maybe because Reed fell off apparently a bunch of times.
Yes,
It's all right.
you fell off in one of the videos, the lab videos.
Good. I'm glad you watched it. That means you watched it.
I did.
Excellent. Somebody's watching my class.
It was
Woo!
really weird because I did like 2 times, so it was like you just disappeared.
Well, yeah, because like there's my head, then all of a sudden it's like boom. Yep, that was me falling. It was, yeah. And then I'm like, well, I could cut that out, but nah, that's fine.
Exciting.
That's good. I'm glad you enjoyed that. Analyte. Hey, that's what's in the flask. More specifically, you could say what's in the Erlenmeyer flask, because generally speaking, if we're running a titration, we're going to use an Erlenmeyer flask underneath, because that's the one that's kind of shaped like a triangle, right? And it's really nice to swirl, which swirling during the titration is a good thing to do. So we'll almost always titrate into an Erlenmeyer flask. Yes, Jake?
So why do we swirl it like specifically? Why don't we just like put a cap on it and shake it like this? And why do we do like this kind of swirl?
Well, I mean, the motion of like mixing it doesn't matter. So shaken or stirred, I don't care.
Okay.
If you're into old school James Bond, but it just needs to get mixed, right? It's much better to have that like forcibly mixed together as opposed to.
Right. So if I wanted to take like an egg beater, I could do that. It's the same thing.
Sure, that's a little convoluted, and I wouldn't recommend it necessarily,
See
but
the results or anything?
but it would not.
Okay.
Yes, Jack.
Scheidler had this thing. It was like a magnet on the thing that was like it spun around in the flask.
Oh yeah, yeah. So you can also use a magnetic stir plate.
Yes.
With
Then
a
you don't have to
magnetic stir.
actually.
Yeah, that's kind of fun too.
That's cool. Are we gonna get to use that?
Maybe
Are we gonna be able to do any sort of like hands-on labs?
if it's gonna happen, it's gonna happen on a Tuesday. So because this is the chem room, which is the only day all week that we learn in the chem room. It is everywhere. We tour the building.
Really? Is it always on second floor?
No.
No,
We're in the library.
We're on the library yesterday,
Yeah,
10 room today,
yeah.
220 tomorrow, 238 the day after. It's a blast. By the way, I've revealed the next vocabulary word. The equivalence point. Now, there's two terms. I have equivalence point and I have endpoint. Those sound like synonyms, but they're not exactly synonyms, okay? The equivalence point is when the moles are precisely equal, okay? The endpoint, which is the next definition, is when the titration changes color. Now, again, they sound like they want to be synonyms, and they almost kind of are, but there's a very peculiar or particular difference that you need to be aware of. The equivalence point is when the moles are actually equal. The end point is when your titration changes color. In an ideal world, when your titration changes color is exactly when you have equal moles. But in practice, if we're doing this actually in a lab, right, when it changes color and when your moles are precisely equal is probably just a little bit off. See the difference? Okay. So in an ideal world, we could always stop it and stop at a titration at the equivalence point. That would be ideal. But in practice, we're using some form of indicator or indication with a color change to stop it, right? And it should be very, very close to the equivalence point, but it's probably not exactly the equivalence point. So we call it the end point. There's two terms, kind of subtle, but just be aware, they are slightly different. All right, so let's eventually get into problems here, but most often the indicator for that, most often the indication that a titration has reached its equivalent point is a color change, but it doesn't have to be. They actually can run titrations using like electricity too, meaning you're checking the conductivity of your analyte. And when the conductivity drastically changes, that's an indication that the reaction is done. Okay, so it's not necessarily just color. You could actually monitor it just by pH too if you wanted to. They have pH meters, right? Where I put the little pH meter in there and it says, oh, it's 1.8. Okay, it's very acidic. And I add base and I add base and I add base and I add base and it's like, oh, it just turned to 7. Okay, that means I'm at the end, right? That's when they are equivalent in theory if I have a strong acid and a strong base. So color change is what we almost always use, but it's not the only way. There's a couple other ways that can get used to indicate your equivalence point or your endpoint for titration. Okay, so indicators are substances that change color based upon their pH. The most commonly used indicator at the high school level is phenolphthalein. Phenolphthalein. Okay, if you're into the spelling. Okay, very strange word. That's the one where at high pH, it's what color? Do you remember? In base, it's bright pink, like crazy bright pink. It's kind of pretty. I don't know, it's a cool color. And when it's an acid, what is it? Try again. An acid, it's what? It's not blue. That'd be more fun though.
Not pink.
It's not pink.
Translucent. Opaque. What do you want me to say?
Well, those are opposites. Is clear a color?
So what do you want? Right?
Oh.
That's such a
Didn't Schuyler do this to you last year?
No.
I think he just
He
said-
didn't harp on that?
No, we barely got through the lessons. We didn't
Wow.
have to do this.
Yeah, I didn't really listen.
Oh my gosh,
I
you
don't
guys
think
are
he
mean.
teased us about it. I think he just like wrote it.
Made Jagger do a
Yeah, that was the day he made me do the lab by myself because I told him he was gonna die soon.
That's not very nice, Trigger.
Well, he was making. No, actually. But I stand by my point.
Wow. Sounds kind of mean. Okay, as part of running an acid-base titration, oftentimes chemists will graph this stuff. Okay, it's pretty common, especially in AP, to look at graphs of a titration. So off to the right there, I have a graph. My y-axis is pH. Okay, you learned about the pH scale last year, right? If it's less than 7, that's acidic. If it's greater than 7, that's basic. If it's at 7, we call that neutral. Okay. And what we have on the x-axis here is the volume of titrant. Now, it says sodium hydroxide because this is just one specific example. But what we have on the x-axis is volume of titrant. I'll just cross that off for now because I think that's maybe a little more all-encompassing, right? Because we're not always adding base. Sometimes we're adding acid or we're adding something else, right? But the moles, or sorry, the volume of titrant added is the x-axis. So what we're doing in this graph, it's pretty self-explanatory, I hope. We have a solution with an initial pH. Now, the initial pH is very, very acidic. So this is a titration where acid is in the flask, base is in the burette. Acid is the analyte, base is the titrant. Okay? So I have acid, and I add some base, 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 and then all of a sudden, boom! Okay, we have this huge increase in pH pretty much within a matter of like 2 or 3 drops. Like literally 2 or 3 drops. It will go from a pH of 3-ish to a pH of 11-ish in like 2 drops. Okay, huge change in pH. Now, in theory, again, we're doing it in the lab, so it's not always perfect, but this is what we call the equivalence point. And I'll abbreviate equivalence. This is the equivalence point right there. Okay, in the middle of this big vertical region in the graph is our equivalence point. That's the spot where the moles of acid and the moles of base are the same. That's the spot where we have perfectly neutralized whatever was in the flask. Okay? So there's a whole bunch of words over here. I could read it to you if you'd like me to, but it's kind of saying the same stuff, right? Y-axis is pH, x-axis is volume of titrant. Okay, we already talked about that, right? So in this example, your sodium hydroxide, which is a strong base, is the titrant. You add it, you add it, you add it. There's a very steep region. This steep region is where the equivalence point occurs. Cool. All right, so another place of importance on the titration graph, I can't speak, is the halfway point. Okay. This is when the titration is over. Right there. That's when it changes color. Okay. Where's the halfway point? Here's the start. Here's where it's done. Where's the halfway point? Yes. Excellent. This is the start. That's the finish. Now, they collected more data, right? Don't let that fool you. This is not the end of a titration. The end of a titration is at the equivalence point when it changes pH drastically. Okay?
The end point is the same.
The end point and the equivalence point should both happen here.
Okay.
The difference is the equivalence point is when the moles are actually equal, which we can't necessarily know.
Yeah.
The end point is when it changes color, but it changes color right here in the big vertical spot.
Okay.
Okay?
Why did it change so like drastically?
Great question. Eventually in this class I will, yeah.
All right, continue.
Okay. It changed. Are you mad at me now, Jagger?
No. Yeah, a little bit. I just wanted to know why I jumped up so fast.
Okay. So
it changed color too, right?
yes, correct. So it changes pH so rapidly because of the logarithmic scale of how we measure pH. All right. So even with a tiny little bit of acid left, okay, it doesn't take actually that much acid to have a pretty low pH. Okay. If I have a 0.00, what would that be? 0.001 molar HCl, okay, that's a pH of 3. It's a pretty low pH and a pretty small molarity, right? Now, when I have a pH of 11, that's 0.001 molar sodium hydroxide, which is also not a very large concentration, but a very high pH. So what happens here is there's just a tiny little bit of H1 plus or acid left over, which keeps that pH pretty low just based on the logarithmic scale and the math that you need to do to solve for it. But right at this moment, the moles are equal, and with just a couple drops of more base, it doesn't take much concentration to change that pH just crazy. So it's partially how we measure pH, because it just doesn't take very large concentrations to get very drastic pH changes. We'll look a lot more at that when we start looking at like particle representations of it. Yes, Jack?
So is there like a better scale that it's measured in at all?
No, the pH scale is pretty darn good. There's not really a different way or a better way to do it. This is the best way to kind of check for acidity.
It's like, in a smaller increment.
Different acids and bases behave different ways. This is a strong acid, strong base titration. Weak acids and weak bases will have slightly different curves that are more gradual and different shapes. Anyway, where were we? Start, finish, right? Where's the halfway point? Well, halfway from start to finish. Okay, please be aware, like I had said, this is the end. Okay, they've collected data well beyond that, but in a lab, it changes color right there. This is the end of our titration. So the halfway point, this looks like it's at like 25 milliliters added. So the halfway would be like 12 and a half, right? Somewhere in here. Okay, that's the halfway point. Very appropriately named because it's halfway.
So one question really quick.
Go for it.
So the end point should be at the equivalence point, but
Correct.
sometimes it just isn't.
Correct. The end point and the equivalence point are hopefully the exact same. The equivalence point is when the moles are exactly perfect. The end point is when it changes color. They're almost always like right on top of each other, right? They're usually very close. If it's a well-designed experiment and you're using the right indicator, it should be extremely close. But again, you remember running titrations, right? Sometimes you add one drop too much. Or it turned like really dark pink and it's like, ooh, I think we missed it. So your end point
Okay.
doesn't match the equivalence.
I just-
Okay. Let's try some math. Some acid base factor label awesomeness. Okay. A student is titrating an unknown solution of sodium hydroxide with 0.3 molar hydrochloric acid. What is the molarity of the unknown sodium hydroxide if 24.45 milliliters of HCl were added from the burette to reach the equivalence point with 15 milliliters of sodium hydroxide? Oof.
Wait, is this the thing that I asked about yesterday with like the
Yeah.
over one? Crazy.
Indeed. Now, when you read this problem, I don't know if the path to solve it is very obvious. Right? Would you agree with that statement? I think you can read this, and in the back of your mind, you might be thinking, huh, oh, I don't know. There's words and numbers and stuff, but I have no clue where to start. That's AP chemistry. Unfortunately, that is kind of a big chunk of this class is reading a problem and knowing what to do. That's extremely tough. So here now, let's go through it together. All right, the first thing that I like to do, and I would strongly encourage you to do, especially come AP test time, I will try to reinforce this with you guys as we start getting ready for that thing eventually. If we don't have a chemical reaction, it'd be really nice to have a chemical reaction of what's going on. So let's start there. My acid is HCl. Okay, it's aqueous. My base is sodium hydroxide. I'm also aqueous. What do you get when acids and bases neutralize each other? What are the products? You get water, yes.
Oh,
Yep.
yeah.
You get water. And then the other stuff, right? Now the other stuff is going to be the sodium ions and the chloride ions from each the acid and the base. So you get water and you get salt. Now, it just so happens that when I say salt for this reaction, I actually mean like salt that you're familiar with, right? Literally sodium chloride table salt. But it doesn't have to be, right? Salt, that term means any ionic compound. Any ionic compound. Those are all considered to be salts. Yes, Ben?
So this, because you have the OH is 1 minus and then the H is 1 plus when the water comes together.
Uh-huh.
So then you consider water to be a salt. Because like that suggests that water is ionic. But then when we were doing the Lewis structure, you were saying it's covalent.
Yes, and it is covalent. So yes, water is not ionic. It just, the charges work out nicely. Okay? But it's not ionic. Water is absolutely covalent. And so is this. HCl is covalent too. That's two nonmetals. So it's a little funky.
Oh, yeah.
Okay? Yes, we're actually blending both covalent and ionic in the same problem, which makes life a little more confusing. But we're not really discussing covalent ionic stuff, so we'll just leave it. I'm going to kind of let it just drift because we don't need it right now. Okay, so here's my reaction. Is it balanced? Yeah, it is. All right, cool. That's nice and easy. We don't have to worry about some weird coefficient thing going on. We got a balanced equation. Now let's read our problem one more time. Let's try to figure out what I know and where I'm going. Okay. The end goal is to solve for the molarity of sodium hydroxide. If I want to solve something about the base, what do I start my factor label problem with? If at the end of the problem I want to learn something about the base of my reaction, what do I start the factor label problem with? The acid. So we want to solve for something base. Let's start with something acid. What do we know about our acid? Okay, we know that the acid molarity, okay, is 0.3. That's one piece of information that we know. We also know that we've added 24.45 milliliters of acid. So we have two pieces of information. Which of those do you like more? Which of those would you like to start our factor label with? The volume of the acid or the molarity of the acid? Volume. The other thing we told you last year, or they told you last year, hopefully, was don't start factor label problems with molarity. Okay? Can you do it mathematically? Yes, you absolutely can. But it makes the labeling of everything kind of annoying, and it makes it a little more complicated. So if we can, in an ideal world, let's start the factor label problem with the not molarity. Sometimes that's volume. Sometimes that's something else, grams or moles, right? But don't start with molarity. That makes life hard. So we've read this, we've analyzed this, we've written our equation, and now we kind of know how to start this just a little bit, right? We want to solve for something base. Let's start with acid. What do we know about the acid? Well, I know I have this much volume, and I know I have that molarity. Let's start with volume. Now, milliliters. Do you like milliliters? Not really, because molarity is moles per liter, right? So if I need this to cancel out eventually, I probably want my volume in liters. Do you have to show me that word? You don't. I don't really care. Now, if you're screwing it up, then I care. But assuming you can move a decimal place 3 spots over, you're good. And just convert it in your head. Okay? I'm going to write it out this time, but moving forward, I'm not. Because I think all of you are capable of moving a decimal place 3 places over. I hope. I hope. So let me convert that. So I have 24.45 milliliters of HCl. I don't want milliliters, so I'm going to convert my milliliters into liters. Okay, and I should put HCl, but that's kind of a generic conversion for any volume, right? So I'm just going to leave that as is. All right. Eventually, I want to get to molarity of base. What do I know about my base so far? Do I know anything about my base? Not yet? Read the problem. What do we know? You're good. What do we know about the base? We know the volume. There's 15 milliliters of base in the flask. That's important. We know the volume of the base. If I want to solve for molarity, what am I missing? If I know the liters of my base, which I do, what do I need? The moles. So the end goal of my factor label problem here is to solve for moles of NaOH. That's the end goal. Because I have the liters, right? It's milliliters right now, but we can convert that just like we did for the other one. I need the moles. So let's get there. All right, so I have milliliters to liters. This is HCl. I have volume of HCl. Where can I go next? What do I want to convert my liters of HCl into if eventually I would like to get to moles of sodium hydroxide? Moles of HCl. Okay. What numbers go here? That's my molarity. Moles per liter, right? For every 1 liter of solution, I have 0.3 moles. That's coming from the problem. Now, this is the part last year where you would go moles of HCl, moles of H1 plus, moles of H1 plus, moles of OH1 minus, moles of OH1 minus, moles of NaOH. Circle it. Does that ring a bell?
Yeah.
Oof, right?
I don't remember.
Well, it's actually the correct way of doing it. Now, here's the deal, right? These are strong. Do these exist like this? No, they exist dissociated.
Yeah.
So really, it should be H1 plus and OH1 minus to get my moles equivalent. But I'm going to let us skip that this year with one caveat. Okay? If you like the old way and it made sense to you last year, I don't care. You can write out as many of those factors as you'd like to. Okay? However, if you have a nice equation and that equation is balanced, we can use the coefficients from that balanced equation just like any other chemical reaction, right? I want to now convert from moles of HCl. Sorry for the lack of space here. Hold on, take two. Okay, I'm going to let us go directly from HCl to NaOH. That was not allowed last year. Last year you had to go from acid to H to OH, OH to base. And every single time. Okay, and there was like way more factors than you ever wanted, and a lot of them were just like 1 to 1 to 1 to 1 to 1 to 1. I'm not going to, you don't have to do that. You're welcome to. Knock yourself out. It's correct. It's absolutely not incorrect, but it's also not much fun. There's my ratio. Right? We balanced this. Well, not really. It was pre-balanced, but we wrote it out, and the ratio is 1 to 1. Acid, base. Sweet. We're good. What do we get? Punch this in if you could. What do you get?
0.007.
Now, if we were actually using sig fig rules in my class, it should be 2. But remember, especially if you were here yesterday or watched yesterday a little bit, 3 sig figs works all day, every day in AP chemistry. Okay? Because on the AP test, 3 sig figs works on every single answer. They will accept it. You know how to do sig fig rules. Okay? When you go off to college, I would strongly encourage you to assume you should follow sig fig rules. But for this class, it's not worth bashing our heads against the wall thinking about it. Answers have 3. Just do 3. Okay? So I'm going to write out 734, I guess it would be. Okay? And that's moles of NaOH. Is that my final answer? No, that's not what I want. What the heck did I want? Molarity. How do I get molarity? Moles over liters. There's the moles. Where's the liters? In the problem. There it is. Now, that's milliliters, right? Again, can you confidently move a decimal place 3 places over? I hope you can. Let's convert our milliliters to liters. And let's set that up and solve for our molarity. I have 0.00734, okay, 335 if you want to keep that number running, moles of NaOH divided by 0.0150 liters. And I'm getting a molarity of 0.489. Cool. All right. Let's try another one. I'd let you try it yourself, except for I'm kind of mean. I'm sorry, did you give me permission to teach? Oh, excellent. I'll take you up on that. All right, let's read this thing. A solution containing 0.5015 grams of sodium carbonate is titrated using an HCl solution. What is the concentration of the HCl if 48.47 milliliters of the HCl solution is added from the burette to reach the equivalence point? Now, this one's a little funkier. First things first, we don't have a balanced chemical reaction for this at all, right? Let's write that out. Let's start there. HCl is the acid. That's old news. We used that one in the last problem. Okay, aqueous. And I'm reacting it with sodium carbonate. What's the formula for sodium carbonate? Nice. Working ahead?
Yeah.
All right. Nothing wrong with that. If you look up sodium, it has a charge of 1+. If you find carbonate, it's a polyatomic ion. It has a charge of 2-. Okay, this is solid. How do I know it's solid? They gave me mass. Okay. They gave me mass of sodium carbonate. Now, here's the deal. What's this? Strong acid. This is an ionic compound. It's salt. But it contains carbonate. Carbonates are bases. Okay? You can write that somewhere if you'd like to, off like in the side or margin or wherever. But carbonates are bases. Okay? So this is an acid-base reaction. It's just one that you've never really seen before. Let me give you an example. Okay? Vinegar, baking soda. Right? That junky late grade school volcano. You add red food coloring to it, right? And it fizzles a little bit, and it's kind of, you never did it? Well, you never lived. Okay? It's really lame, actually. Don't bother. So vinegar is acid. Baking soda is sodium bicarbonate. Just different by one little thing, all right? But it contains a carbonate. It's a base. They react. Now, what it produces is water. That's still true. Okay. Salt. That's still true. Our salt in this instance is going to be NaCl again. That's aqueous. And then it produces one extra product. Okay. Your little volcano with vinegar and baking soda bubbles. What are the bubbles? CO2. Carbon dioxide gas. Okay. So when carbonates react with acid, you still get water, you still get salt for the products, but you get one extra thing. You get carbon dioxide as well. This is not balanced. Go for it. This is like real chemistry. I love it. Fun. Or not.
Yeah, I have a question.
Yeah.
On that,
Uh-huh.
22, is that like 22 minutes?
The A?
No, the 22 MIN.
Yeah.
What does that have to
Yeah, that's the half-life. So it breaks down. It effectively decomposes into a different element. And then, you know, gives off radiation in the process. A is annuals. So yeah. Yeah, it's kind of, if you look at the top, right, this is, it's a multi-use, like, international periodic table.
Oh, yeah.
So they don't use years or whatever, they call them annuals, but yes. Did you balance this thing? Oh,
I got this.
what do I need? I don't want to think, I trust you. How many of these do I need? Okay. Is that good?
Yeah.
That's it? That was easy. Okay. Thought it was more spicy than that, but never mind. All right, so we have a balanced equation. Now, what are we trying to solve for? What's the end goal? What is the concentration of HCl? Concentration is molarity, right? We're talking about solutions. There's more than one way to measure the concentration of a solution, but for us, it's molarity, okay? Moles per liter. That's the end goal. So we want to solve about the base. What do I start my factor label problem with? I was looking for more generic than that. If I want to learn, or if I want to solve for something about the acid, I should start my factor label problem with the base, right? Whatever you want to know, or wherever you want to end up, start with the opposite. In the previous problem, we needed to know the molarity of base. So what did we start our factor label problem with? Acid. In this one, we want to learn about the molarity of acid. So what do I start my factor label problem with? Base. Okay? So what do I know about the base? Well, I know the mass. That's it. Okay, looks like I'm starting with the mass. I have 0.5015 grams of sodium carbonate, Na2CO3. Where can I go from grams? Moles. Okay, now what numbers go here? It's the molar mass. Cole's got this. Cole's like, you're on next week's curriculum. Good job. Not actually, but this is molar mass, right? How do I find a molar mass? I use my periodic table and I add all those things up. So, what was it, Cole? 105.99. Okay, that's the base. I need to get to acid, right? Now, I want molarity when it's all said and done. What do I know about my acid so far? How many what? What do I know about my acid from the problem? Volume. I know how much there was, right, or how much I used, I guess, right? We're titrating with the HCl, so this is the titrant. I know how much I added from the burette. I added 48.47 milliliters from the burette. I want to solve for molarity. I have volume. What am I missing? Moles. Let's solve for moles. So moles of base, let's convert that to moles of acid. The ratio. Okay, this is huge, isn't it? If we hadn't written out this reaction, how was this going to go? Yeah, you'd probably just write 1, right? Because that feels like the low-hanging fruit more often than not. Just everything's 1 to 1 to 1. But sometimes it's not 1 to 1 to 1. Okay? So, good thing we did this. We have a balanced equation, and we see that the ratio is 2 acids for every 1 base. Let's solve that. How many moles of HCl do we get? Yeah, total. No, you're good. I'm getting 0.00953108878. Not that we don't want all those digits, but blah, blah, blah. Okay. Am I done? Oh, what'd I do? Oh, you know what? It's 0.5015, not 0.5051. Thanks, guys. See, this is why I like doing it live. What was it?
0.0095.
Okay, cool. Let's try that again. All right, sweet. So I'm not done. I want molarity. So give me my moles over my liters. Now, milliliters was 48.47. So in liters, I move that decimal place 3 spots over, right? I go 1, 2, 3. So 0.0 0.4847. And our final molarity is, I'm getting 0.195. Okay, kind of old news a little bit, right? A slight little tweak from last year, obviously. I'm not making you do all the ones and ones and ones for the moles, mole. Okay, but if you're not doing the one-to-one nonsense, you have to do a balanced chemical equation. Because again, without this up top in green, we could not have gotten that third factor correct. Okay, so that's the difference between this year and last year. Last year, we didn't necessarily use a balanced equation always, because if you go from moles of acid to moles of H, you see the ratio in the formula, right? If I was going from moles of HCl to moles of H, that's 1-to-1, because there's one H in my HCl, right? So you don't need the three factors of the craziness that we taught you last year, but you do need a balanced chemical equation to avoid that. Because without a balanced equation, you can't just assume it's 1-to-1. It might not be. All right, 3 more problems on here. We're very clearly not going to finish that today. That's okay. I didn't think we were. We would. We were. We were. I didn't think we were. But let's try all these. They're all kind of using the same context. They're all antacid tablets. Okay. We have a Phillips tablet, which I'm sure you're not familiar with. Tums, that one sounds familiar. Rolaids, maybe that one does. Does that sound familiar? They used to have a commercial. ROLAIDS spells relief.
That doesn't spell relief.
Okay. But what we're doing here is I have the same molarity of stomach acid, HCl, at a molarity of 0.155. And what I'm asking is how many milliliters or how much volume of stomach acid can each of these different heartburn or antacid tablets neutralize in your stomach? Okay. Now, why don't you see what you can do in the next 5 minutes to set this up, and I'll pick it up to start class tomorrow. I've shown you 2, okay? The first one is nice because it's MgOH, MgOH2. It's magnesium hydroxide. It's a normal acid-base reaction like you're used to. Okay, the second one uses a carbonate, and the third one uses some crazy, weird, wacko formula that has a carbonate and OH in it. So we'll leave that one together tomorrow. But see what you can do on number 3A, and then I'll pick this up and show you to start class tomorrow. And you're welcome to chit-chat with each other if you need to. That very clearly goes for people in human form, not on, computer screen form.